In the context of Markov chains, a transition is a move from one state to another. Here's a transition probability. This is the chance that you are at state J tomorrow, given that you are at state I today. And it is called a one-step transition probability. One step because you're taking one step from time n to time n plus 1. Transition probability because you're making a transition between two states. And this probability depends on three quantities. It depends on the starting state I, the ending state j, and also on how long the chain has been run. So it is the one-step transition probability at time n. However, for many chains, there is a simplification. Consider, for example, the what is called the simple symmetric random walk. Say you start at 0, and at each step you essentially toss a coin. You go up 1 or down 1. With probability half each. So if you make this move over and over again, and I tell you that, at some point you got to level 72, then where are you going to be after one more step? You will tell me immediately, I'm going to be at 71 or 73. You don't have to ask me, well, how long have you been running the chain till you got to 72? It doesn't matter. The transition probabilities don't depend on n. And in this situation, the one-step transition probability, which we are almost always going to shorten to just transition probability, can be written as the chance that x1 is equal to j given that x0 is equal to I. And you can start measuring time at any point. And so we will denote this quantity by p I, j. That is understood to be a conditional probability. Given that you are at I today, what is the chance that you are at j tomorrow? And these transition probabilities can be collected into a transition matrix. Which we'll denote by capital P, and its ij element is this one-step transition probability that we've just defined. So P is a square matrix. The rows and columns are indexed by the states. These transition probabilities make it easy to find probabilities of paths. A path is a trajectory. It's a sequence of states that your chain visits. So supposing you start at I naught, so then naught represents time 0. From this, the chance that you go to I1 followed by I2 followed by I3, you can calculate as follows. You're starting at I0. In one step, you have to get to I1. Now, from I1, you have to get to I2. Markov property, you don't care that you came from I0, you just go from I1 to I2, and then to get to I3, you had to, in one step, get there from I2. And so if you have these transition probabilities, you can compute the probability that the chain takes any particular path.